Hi everyone. Today we are extremely delighted to have Professor Thomas Vidick with us, someone who needs no introduction. However, here is a brief introduction. Professor Vidick is a professor of computing and mathematical sciences at the prestigious California Institute of Technology. His research interests are broadly in quantum information and cryptography, using the tools of complexity theory. He was a postdoc at MIT under Professor Scott Aronson and completed his PhD at UC Berkeley under the supervision of Professor Umesh Vazirani. Professor Vidick is also a recipient of Presidential Early Career Award. Today, we will talk about research, quantum computing, and some more exciting topics. Let's get started. First of all, I would like to thank Professor Vidick for accepting our invitation and making the time in his busy schedule to talk to the students and also talk about his research career. So, yeah, so how are you, Professor? And first of all, good morning to you.
Yeah, good evening. I'm good. Thanks for inviting me. It's a pleasure to be talking to you and to anyone else who's watching.
So I guess I will just jump to the questions directly. And so the first question I would like to know is, so I know that like your research interests is in quantum information and cryptography. So, but can you elaborate it more and maybe for the audience who is watching this, consisting of high school students and undergraduates?
Okay, so for someone who doesn't have background in quantum computing, my research is in quantum computing, then I could make it more specific. So what's quantum computing? It's studying the power of computing devices whose functioning is based on the laws of quantum mechanics. So most computers, the physics that describe how they operate is just classical physics, because information is represented as a microscopic property, is just current, and the current involves many electrons. So starting in the 1970s, researchers starting in physics realized that the quantum mechanics, which is the physical theory for the infinitely small, before that, quantum mechanics is just a strange theory that people are grappling to understand, but they realized that it had a potential for computing. And the way they realized it is that first they realized that quantum mechanics was hard to simulate. So this is physicists trying to make predictions. They have to make calculations, and these calculations are just absurdly hard because quantum mechanical systems have a very large number of degrees of freedom, and it seems that you need to model all these parameters in order to understand what the system is doing. And then in the 70s, Feynman, who was professor of physics at Caltech, which is where I am, kind of flipped things around, and he said, well, if these quantum systems are so hard to simulate, why don't we start trying to engineer quantum computers, quantum systems that are used to simulate the quantum mechanical, physical systems that we're interested in simulating, because then you're using quantum mechanics to simulate quantum mechanics, and then you lose this. You no longer have this problem of exponential overhead that you have if you try to do classical simulation. Okay, so he suggested that. And then, okay, good idea. I think not that much happened for a decade or so. And then in the 90s, researchers in computer science started getting curious about the modeling, including my PhD advisor, Umesh Vazirani in Berkeley and others. And they started playing around a little bit with what could you do from an algorithmic point of view, and discovered that there seemed to exist very specific problems for which you could develop much faster algorithms if the algorithm is made to run on these quantum computers who have different laws of operation. So the information they manipulate is not bits, it's qubits. You have superpositions. Okay, I'm not going to lecture about quantum computing, but and so this builds up to the famous quantum algorithm for factoring, polynomial time algorithm for factoring, and that suddenly, once you have that discovery, like, okay, everyone wants to understand what's going on, right? So so then the field got bigger and bigger. And now it's a very large field, quantum computing. There's a very large theory of quantum information, just Shannon theory, but in the quantum, just understanding how much information can you encode in quantum states and what can you recover and what's the best error correcting codes, things like this. What I work on is complexity in cryptography. So in complexity theory, we try to understand maybe the limits of quantum computers and how the use of quantum information affects like standard complexity classes like P and NP and P space and all these complex. If anyone knows complexity, they have quantum analogs, and we try to understand the relationships between them. And in cryptography, it's the idea of trying to use quantum information to achieve secure communication in a better way than classically. This also was discovered even before algorithms for factoring. So in the 80s, people discovered that if you used quantum information, you could use special properties of quantum mechanics, such as there's something called no cloning principle. That's the idea that quantum information cannot be copied. So classical information can always be copied in principle, like 0, 1, you copy, you get 0, 1. But quantum information, because of its nature, cannot like fundamentally be copied. And once you know that, and if you know a little bit about cryptography, you kind of want to say, okay, I mean, that sounds kind of useful. And the way it's used is that you can send messages encoded in quantum information. And the fact that they cannot be copied means that if someone tries to read the message, get information from it, then they must perturb it. Because if they could get information without perturbing it, they basically have copied. The information would be in the original message and in what the attacker.
And that's not possible.
And so that can be used to, have then that can be detected. And so that leads you to the design of cryptographic protocols using quantum information that don't rely on computational assumptions. And so that's something that I also work on.
Oh, that's quite interesting to know. So yeah, the history of, like, I heard something about a Feynman starting to simulate quantum computers, but I didn't know it has such a interesting history. So like this brings us to our next question. So when did you get to know about quantum computing, and when did you think that you should pursue a career as a researcher in this?
Pretty late. So what happened? So my path is both typical and slightly atypical. So I was okay. I went to high school, apparently some people who are listening, and then I did my undergraduate. I was specializing in math, in pure math. I did number theory, algebraic number theory during my undergraduate. I did a little research there. And then I liked the math because it's very beautiful. It's so elegant, and you just want to figure everything out. But at some point, I had a little bit of a personal crisis where I realized that even though I enjoyed the beauty of it, I had kind of personally lost track for why I was studying this or that question. I didn't know anymore. There were all these like beautiful questions, but then how did it relate to things that I live through every day? I didn't know. It felt disconnected to me. I'm not saying this is true of math in an absolute sense. It was just how I felt. So I took a year off. I did very different things. And then after the year off, I wasn't quite sure what to do, but I thought, okay, I'll try computer science because, maybe this is more connected to reality, like connected to computers and how things function, computing. And so I did a master's in computer science. And the best class by far in the master's was the quantum computing class, which was taught by Julia Kempe. She was a researcher in the domain. I just found this extremely exciting, and for me it was the perfect thing in the sense that I really like the math behind quantum computing. I like linear algebra. I like operator spaces. I like these things. So I thought, okay, great. Like I love this math, and at the same time, it seemed like among the whole of computer science, it was the best topic for me because it was the one that kind of most directly addressed the nature of the world in which we live in. Like if you build a theory of anything, such as computing, for example, you want it to be grounded in the real world. If it's some totally abstract thing, it's fun, but to me, it's less relevant. So I want to be grounded, and what's the best theory? It's quantum mechanics, and now you had everything at the same time. I had like physics, the real world in a way. I had the pure, beautiful math that I loved, and I had these questions about computing that connected them. And so I thought, okay, this is great. This is what I need to do. So then I did the master's, and then I did in quantum. So I had one class on computing, and then I did a PhD in quantum computing in Berkeley. And then you said what I did after that. Yeah.
Okay, it's a really atypical part, I should say. How you started with algebraic number theory and landed up into quantum computing. Yeah, that's
the what do you say, the takeaway, the take home message is like, be open for surprises. Okay, so it's very, very unlikely that what you think you want to do right now is actually what you'll do, or what you still think you want to do, even just like 2 years or 5 years from now.
yeah, maybe I should like add something on myself also. This is something happened to me also. When I was in high school, I thought that I should do maths, and I was like interested towards calculus and like doing number theory and everything. But after joining CMI, I thought like maybe okay, let's try something in CS also. And then my interest diverged into complexity theory and cryptography and all. So yeah,
Yeah.
I took one courses and it was really amazing. And I thought, okay, that's what I want to do now.
Yeah. I think we're also very influenced by our mentors. I think in my case, like
Right.
the decision was just that the person teaching the class was a great teacher, and it was very motivating, and her enthusiasm for the field, communicated to me, and I think that had great influence.
Yeah, that's absolutely correct. So it seems that like you like quantum computing a lot, and you have like as you said, like quantum computing is something which you can relate to your natural life and everyday life. So what is one of your favorite work or result which you really like something that you should have always dreamt about? Okay, that's something I wanted to do. Is there any something one result of you?
Okay, that's a good question. So the results I like, they tend to be more theoretical in the end, because I like when things are very elegant. Um, what's my favorite result? Like, there's a beautiful result in quantum complexity theory, since I do quantum complexity theory. But it's more advanced than the audience maybe, but it's the characterization QIP equals P space. So these are headline results in complexity. You take two complexity classes, QIP, quantum interactive proofs, and P space is polynomial space, and then you put an equal sign, and these are it's like E equals MC squared or something. So, but it's the complexity theory version. And what's beautiful about that result is the way it was arrived at. And so I was a student at the time, and over like 3 or 4 years, every year there was a new paper making progress towards the question. I think it left a lasting memory on me, just seeing how people were, it's not like you have this result and you want to prove it. First of all, you don't know if it's true or not. And secondly, it seems like you're never going to be able to prove it. And so you do like small steps, and then suddenly each step opens a window onto the next step, which opens a window onto the next step. And you didn't see it coming. And that result is one like this, where you didn't see it coming. There were small steps, and then suddenly enough windows were open, and it worked. And it worked together. It's also a very beautiful result in terms of its proof. It uses semi-definite programming, which is a optimization technique that's used a lot in quantum computing. But this is one of the first results that was using it, and it used it in a very, very fine, subtle way. So you couldn't. That's not a result that you could prove by just applying hammers or something. You had to really understand and model properly the situation. Some of the earlier papers modeled the situation in a certain way that just didn't get there, and then they flipped it around and flipped it around the second time, and then eventually were able to prove it. Yeah.
So did you have any conjecture while working on that problem that okay, it might be something like this?
This is not my result. So I'm not talking about my result. This is someone else's result. And no, I think it's also a surprising result in the sense, even like maybe slightly I don't know if it's disappointing. I don't find it disappointing, but it's a result that says that in a particular setting, this setting of interactive proofs, the use of quantum information does not make any difference. And so in that respect, it was surprising. People expect that if you take almost any model and you add quantum in front of it, then hopefully it should be more. Just because in general we don't expect. I don't think people expect that quantum computers can be simulated by classical computers. So quantum algorithms seem to be more powerful than classical algorithms. But these interactive proofs, they're a step above. Like it's not polynomial time algorithms. It's a step above in the hierarchy of things. And their quantum information didn't make a difference. But if you're going to prove that, you're not going to be able to prove it just by direct simulation in a way, because if you do direct simulation, you have an exponential overhead. It's not going to work. So I think I don't think I think it arrived by surprise. I don't think that people wanted to prove this when they started. They just wanted to understand the situation, and then slowly they realized that, oh, okay, maybe you can prove this.
So as you said, like some problems which people were not expecting to be true, but it turned out to be true. So so how do you like generally decide that okay, which problem you should look upon, like which problems are interesting for you, or like which problem do you think are can be tackled?
Yeah, that's a good question. I mean, that's a hard question. I think first of all, you have, this is what I was saying earlier, maybe I need to know why I want to work on the problem. So there needs to be, I need to make sure I understand. I think most people, I don't know, I think most people maybe have some like very long-term driving problems. Like there's some area that you want to understand. You want to understand how some pieces fit together. It's not necessarily a result that you want to prove, but you just want to understand the landscape of things, and maybe there's some slightly vague question in the background that you're trying to address, and then you choose problems that you feel help you make progress towards that question. So this can be very, very indirect, because if you knew how to get there, you just that's it, like go and get there. So maybe some mathematicians sometimes, or there's a big conjecture that you just want to prove, and you have a strategy for getting there, and you just follow that strategy. I think that's not the typical case. The typical case is that you don't really know what you're doing. You just have some intuition, and you select problems based on how they help you develop this understanding of an area. So that's one way of selecting them. Another way is I think you do need to select problems where you feel that you have an edge, like things that you feel that, okay, because of your background or things that you've done before, you think that you're going to be able to make progress on the problem. So usually you have many problems in your head but you spend maybe 10 minutes on them, and then or an hour, let's say, max, and then you just don't really have an idea, and so then you just shelve it, right? You keep it on the side, and you just wait until like ideas pop up. It's also the case that in practice, a lot of problems arise from discussions. So it's not that you have a master plan in your head that you're going to work on this or that, but in pre-COVID times, you travel and you talk to people and you have all these discussions, but even at school with your friends or your colleagues, and then the interaction, I think, is important. Like someone will ask a question, you feel, okay, maybe I see the question differently, and then you have a discussion, and then some problem pops up, and then it feels like an interesting problem, and you continue thinking about it.
So you just now mentioned that sometimes there are some problems which you think about for 10 minutes or 1 hour, and you don't think that okay, there is any way to solve it, and you keep it aside. But sometimes it may be the case that okay, you like a problem, you start working on that, but after some time maybe you are stuck at a point. So has it ever happened to you? And if it happened, then how did you overcome that feeling of okay, like I'm not able to make any progress?
Yeah, I mean, it happens all the time. Obviously, that's the steady state, right? I think I'm not the right person to ask this because I'm pretty bad about it. So I'm very stubborn, and so I can, yeah. I mean, 1 hour it's what I wish I was able to do, but usually it's more like 6 months. Just trying to solve a problem and not making progress. Well, okay, one thing that I do for myself, so let's say I really care about the problem, so I'm willing to spend 6 months or a year or more. I mean, there's some problems I've worked over many years and I still haven't made any progress on them. When I started my PhD, the first year and a half or something, I was working on the same program the whole time and I made no progress at all. It was very depressing. Because I felt that okay, like if I don't make progress in a year and a half, why would I make progress the next year and a half? Okay, so there's two things that I do help me there a little bit. One is just make sure that I feel that I'm learning. So I might not be making progress towards that problem, but at least I'm doing one thing that I enjoy just for its own sake, which is learning. So I always this is a recommendation which is that I try to give to my own students because they tend to just want to solve the problem they're bothered with, and so they're very focused, and they just want to solve that problem, and so they'll look at things that are directly related to it. I try to push myself as far as I can from that strategy by recognizing that it's important to be much broader than that, and you don't know where the idea is going to come from. And if you look for the idea just where you think it is, that's not going to work because you don't know where the idea is. Okay, so you have to force yourself to be a little bit broader and read things that are distantly related, and attend seminars and pick up a book and read some other papers. And you might not see the connection at first, but as long as you enjoy it, you feel that you're learning something that might be useful in the future, you're not wasting your time. And maybe the idea is going to come, over a couple of years or something, like who knows where the idea is going to come. So that's one thing that I do to not feel too frustrated. And then the other thing is that at some point you have to give up, and you shouldn't be sad about it. You're not giving up for life, you're giving up just for now. Okay, like it's a bit like what happens in your sleep. Like at some point you have to give up, you're just too tired, right? You go to sleep, but you don't want to go to sleep. You want to, have fun or read or go see a movie or whatever. But your body says, look, you need to sleep right now. And then we know that the sleep is important. Like memories form, and you get lots of dreams, you have lots of ideas, you process things, and the next morning you're a different person. And so I think in research you also have to accept that sometimes, it's not sleep, but it's after a few months. You have to say, look, like, let me just write down where I am. Maybe I'm nowhere or something. Okay, so then I'm just writing down that I'm nowhere, writing down the ideas I had, and then I take a break. And this break could be a 1 month break, could be 6 months, could be a 2 years break. And it's not, you'll get back to it for sure. You'll get some idea later. If you worked on the problem for a year, you're not going to forget it for life. And it'll come back later. But you just accept that right now you're not the person who's able to solve it. You're not thinking right. You have to take this break. And then for sure, this is going to work. Like it's going to come back to you, and you'll have an idea. It's a like completely unexpected moment, and then you'll get back. You'll get back to it. But it's really hard to do this because you always feel like just one more day, okay, one more day, and I'll have an idea. I wasted so much time on it. This investment, it needs to pay off. Okay, but that's just the wrong strategy. But it's hard to accept, but it's the wrong strategy. So you have to let it go and come back to it later, not tomorrow, later.
That's a really great advice, and I think our audience should also learn from this advice that you should sometimes let things go and come back to it later on. And I like that point of that we are always learning meanwhile. We're not like losing something. It's
right.
In future we are learning something. So that's a really great advice for the audience. Now I would like to ask you, if you could travel back in time and meet your younger self sometime in maybe grad school or masters or undergrads, what will be some advice which you would want to give to your younger self?
I think relax. So don't take yourself so seriously. A little bit in relation to what I was saying, it's not, it's good to be driven and to organize yourself and do things, but that's not how you make the most progress. You make the most progress by enjoying yourself and doing the things that you like. And I think we're all people here, researchers, the audience, pretty intense about what we like doing, what we want to do, and so we'll work hard, spend lots of time like reading, learning, doing exercises, doing research problems, and that's good. That's important. You need to build those skills, but you also need a lot of air. Life is long, and there's many things that you need to be developing at the same time, and all these things will enrich each other. And so I think that in grad school, I personally, this is not the case of everyone, but I personally was a little bit, was pretty obstinate. Like I did my undergrad in France, And France is a pretty balanced country, so people stop, don't go to the office in the weekend, and they do many things. And I had a pretty balanced life. And I moved to the US, and the US is a more intense country, and grad students in France take a lot of breaks. Grad students in the US, work a lot. They also have a lot of fun, but they do work a lot. And I think I took it a little bit too seriously. And so, yeah, I would recommend not doing that. I mean, nothing bad happened, but it's really not necessary. So
what are your hobbies now? Like, what do you do after, like, for taking a break during research?
I'm an outdoors person. So here in California, it's really nice to be hiking or biking. So most of my breaks are just going to the mountain, and I have a bike. I bike in the mountain a lot. I also go on longer hikes or weekend trips to the parks, things like that. And that I find gives me a lot of air. I need to see. It's really wonderful to be able. So here, I'm right next to Los Angeles. There's many bad things about Los Angeles, but there are also many good things. And one of the good things is that it's very open. On one side of the city, you have the ocean, which is wonderful to see, and on the other side, you have really wonderful mountains that go to I know 3,000 or 4,000 meters. There's snow at the top, and the bottom is super hot. And I like this openness, so this is what I'll do. I'll just and then I read a lot, just for pleasure.
Okay, that's really great to know. So we have discussed so far about how research is and everything. So maybe let me get something particular about your interests. So for the past few years, we have heard a lot about the quantum supremacy race. Like we have read articles and YouTube videos, and like how Google, IBM, Microsoft, and lot of new startup companies are also building quantum computers that can perform some really great tasks and what have been studied for in theory for the past years. And also scientists at like high sophisticated labs are demonstrating the experiments, and there's a lot of things going on. So what are your views on the future of quantum computing? How do you see quantum computing in the next decade or 2 decades?
Let me correct one thing that you said. So, okay, I don't remember what you said exactly, but you said people are building quantum computers that can accomplish really great tasks, or you said something like this.
Yes.
I'll correct this. I'll say people are trying to build quantum computers that at the moment cannot do anything useful or great, but maybe in the future might be able to do useful things. Okay, so the current there's both something extremely impressive in terms of what. So when I started, I was saying I started in my master's. So this was in 2007. So it's like almost 15 years ago. There was no quantum computer. There was not even a 1-qubit quantum computer. Okay, this was you couldn't like nicely manipulate. You could do cryptography, which is prepare quantum states like in a static state and then measure it, but you couldn't operate on it. Then maybe 5 years in, people started making like 1 qubit, and now 10 years more, suddenly things have taken off. So there is something extremely impressive that is happening right now, which is that's it. Somehow the experimental side of the field has taken off, and people are building computers that have not 0 or 1 qubits, but that have 10, 20, 50, 100. And that's extremely impressive, and I expect that to continue. Now, in spite of it being impressive, you have to look at the fine print somehow. And when people say that, oh, we have a 100-qubit computer, they probably don't have 100 qubits, and they definitely don't have a computer. What they have is that something that it seems like maybe it has roughly. The problem is that it's not even clear how to measure how many qubits you have, because the question is, what can you do with them? And these things usually, they fail very quickly. If you try to operate on them, there's a very large amount of noise. If you try to operate on 2 of them at the same time, there's even much more noise. And so it's the kind of circuits that can be run on the circuit on the devices are very, very limited, and there's no useful computation that's been done on the quantum computer so far. There's only things that look like they cannot be simulated if you're naive, but every time this happens, like the Google supremacy experiment, people look into it a little bit more and they become less naive, and then they're actually able to simulate it. So okay, so that's just to say that at the moment there's both something really impressive that's happened, and at the same time, from the point of view of computation, you could still say, with blank face, nothing has happened. Everything can be simulated. Okay. I don't expect that this will last. I expect that within 2 or 3 years, it will no longer be the case. So within 2 or 3 years, we'll have, truly convincing demonstrations of what's called like quantum advantage, which means these quantum devices will have accomplished some task that people really truly don't see how they could reproduce the same classically. The problem is that this cannot reproduce the same. It's a little bit subtle, because one difficulty that you have with the quantum device is that you don't actually know what you're doing. You have a model for what you're doing in your head, but it's so noisy that you can't calculate, you can't model what it actually is doing. You can only observe it. But what you observe are random outcomes, and these are distributions over many bits. And so these random outcomes, you run the machine, you see one outcome. Okay, you run it again, you see another outcome. You run it again, you see another. Okay, you just see different things all the time. And so what do you know about? So there's a whole challenge here, which is also a theoretical challenge, which is that if your device cannot be simulated, how do you test it? Like it's just returning outcomes, and if you can't predict what the outcomes are supposed to be, then if it factors, then you can check. Okay, if it solves an NP problem, you can check. But there's no factoring in the next 10 years or probably more for sure. So in the meantime, we're solving tasks that are not obviously easy to verify at all, and so that's a challenge. Okay, for the next 10 or 20 years, I think things are going to improve. I think actually right now there's sort of two axes. One is the size axis, where people are building bigger and bigger machines and trying to do these supremacy demonstrations, like the Google experiment, where I think it's a bit shaky right now, but in 2 or 3 years, this will have been demonstrated. And another axis is not focusing on size, but is focusing on quality, trying to implement devices that have just like a very small number of qubits. But maybe there's some error correction that's built in, and so trying to demonstrate error correction and fault tolerance on just 1 or 2 qubits. This is currently a challenge, but it's a challenge that's being solved right now. Like the most exciting experiments these days are about trying to implement fault tolerance. They haven't yet implemented fault tolerance, but I think again, this within 2 or 3 years will have been demonstrated on a small size. And then the next step is to put the two together. You want a big size and you want fault tolerance, at least maybe not fault tolerance, but some form of error correction so that you can run larger circuits. I think this will take time, but at that point, it's really an engineering, it's a very challenging engineering problem, but it's an engineering problem. So 10 years, I think, is a little bit short as a timeline, but between 10 to 20 years, I think this is when we'll have quantum computers that can solve real algorithmic problems, as opposed to these supremacy things, which are just sampling tasks. They're not the way you have to be very careful how you define it, and then it's not, it's just meant to impress everyone, but it doesn't solve any useful problem. So but I think if we, in the 10 to 20 years regime, this will, in my opinion, this will definitely happen. There's always people who are skeptics, but they tend to be people who don't necessarily follow the field too closely, or on the opposite hand, physicists tend to be extremely optimistic, and so they're usually just too optimistic because this is how they get funding. So I wouldn't follow a physicist's predictions. They would predict that in 5 years we're done. But anyways, I think 10 to 20 years is the correct timeline, which I wouldn't have predicted when I started in the field. By the way, when I started 15 years ago, it was really, there were all kinds of guesses. Some people might say 10 years, but that would be rare. But some people might say 50, some people might say never. It was really unclear. Now I think there's much more of a consensus around, some people might say 5, 10, or 20. I think no one says 50. 50 is too big, too far. And no one says, 1 year either. Clearly, 1 or 2 years, we won't be running algorithms yet. But yeah.
So maybe.
Sorry, go ahead.
Yeah, so I was just asking, like, maybe to put in perspective. So if we compare the generation of classical computers, so classical computers with quantum computers. So which generation do you think we are in quantum computing? Are we in first generation, second generation, or what is it?
Oh, I don't know this terminology. Is there a terminology of first generation, second
Yeah, I
generation?
don't. Yeah, something like in first generation, there were the basic computers, which is the Turing started and everything. And second generation with transistors, and third generation with integrated
No,
circuits and
no, we're
something like
before all that. We're not even at the first generation. So we're not even
that.
at
Oh, okay.
these, the computers that were used during the World War II, and so we're before,
Okay.
um, we're before that. I think definitely not transistors or anything. I mean, because when you say first generation computer, I think they did solve some useful tasks. They did do some computations that were useful
Yeah.
as scientific computations. Then they did do some number crunching for breaking codes and things like this. So currently the machines, they don't do anything useful.
Okay.
We're within the next 5 years, they might start becoming useful at some really targeted problems in physics or chemistry, not like computational problems, but simulation, where there's a little bit less of an overhead because you're starting from a quantum system, simulating it to a quantum system, and if you choose the right platforms, then noise might be okay, and you don't need to control everything too precisely. And but I think that would be generation 0.5 maybe, so something like this. So but then what I also think is that it's going to speed up much faster, right? Because a lot of what's been learned in constructing transistors and building architectures for computers, all this can be reused for the quantum computers, because the same problems, the low-level operating mechanisms are different, but the high-level structure is the same. There's a processor, there's a memory, you need communication between these things. And so there's a lot of knowledge that's been learned, and even the equipment, like factories that make chips and stuff, these things can be reused. I think it's going to go much faster once we get to some critical point, which we're basically
Yeah.
getting at now, so or in a few years.
Okay. So that's really good explanation, and I think now our audience will definitely try to look upon it and read more quantum computing. So there have some questions we have been receiving. So do you have any suggestions for our readers to begin off with quantum computing? And uh, yeah,
Well, I have to say, so if you haven't looked into quantum computing yet, there's a very popular and I think very good Coursera or edX. So there's a course by my PhD advisor who's a senior, so Vazirani. So if you Google like Vazirani quantum computing Coursera or edX, I forgot. There's some nice like video lectures and also lecture notes that he has that are very good if you have a little bit of background in computer science, no background in quantum computing. They're a great resource. There's also a good textbook by Nielsen and Chuang called Quantum Information and Computation. It's available. In fact, there's it's Cambridge University Press, and there's an Indian edition or something, so you can find it. I bought a copy when I went. I was talking to Amik before, and I visited CMI and IMSC 15 or so years ago, and I bought my copy of the quantum computing textbook in India because it was cheaper and it was the same book, and I brought it back with me to. I was still in France at the time, so that book existed 15 years ago, but it's still a very good introduction. So quantum information.
okay.
So I would start this by the videos and the book. Yeah.
And so finally, I just one question. So do you have any general advice for our audience who are in their first steps of becoming researchers?
Um, uh, I think you should enjoy yourself. So I think you should make sure that whatever you do, you know why you're doing it. This is what got me stuck. So I needed to know what I'm doing it, and you're enjoying enjoying it. And this is not so easy because we all have a certain background. Okay, we all have parents, we have friends, we have a family, we have a society that we live in, we have a school, we have a religion, maybe, and all these things they put expectations that you want to be a doctor because of your parents, or you want to be a priest because of your religion, or you want to be a soccer player because of your friends, or maybe because of the girls, or something like this. Okay, so. And so there's a lot of fabrication like this, where we think that this is what we want to do, but you have to ask really hard the question: okay, is it really what I want to do, or is it what someone else wants me to do? And because I was raised in that environment. Okay, so And I think the best way to do that is to really truly like look deep inside yourself and feel, okay, like when am I happy? What do I enjoy? What brings me pleasure? And also what brings me fulfillment? So that's a little bit connected to the what's important for me, what are the important questions. And so I think it's very useful to pause and to try to explore that, and to do it, feeling happy about it. It's a happy question. You have a whole life ahead of you, and this life is going to be happy. And so you just okay, and then you do that, and then that will help you determine, if you want to do research, what's really the kind of questions that you're excited about, that are important for you, and that make you happy. And if you find that, importance, excitement, happiness, then you just have a great career ahead, because you'll just be motivated the whole time.
Right.
Yeah.
So thank you for this kind advice. And it's something I would like repeat to my audience once again. You should think that what you want to really do. Yeah, like there's societal pressure and family pressure and lots of other things, expectations from people, but you should really do what you want to love to do. And as you saw in our interview, Professor Thomas started with algebraic number theory and other things in math, but he wanted to do quantum computation and he's doing really great in quantum information and everything. So yeah, so if you like what you do, then definitely that's a good path for you. So with this, I think we can conclude our session with Professor Thomas Vidick today. And it was lovely talking to you, Professor. We learned a lot of things about how to do research, how to take decisions in our life, and definitely a lot about quantum computing. Definitely, what people knew about quantum computing, now they know a lot more about it. And I'm pretty sure that our audience is now highly motivated to go upon and read about quantum computation from Professor Umesh Vajirani's videos and a lot. And I hope that you all liked the session. So thank you, Professor, once again for accepting my invitation and making time to talk to you.
Thanks a lot for organizing this and inviting me. It was a pleasure. Have fun, everyone.
Thank you. Thank you once again.